They appear out of nowhere and threaten our very existence. From rocks crashing through homes to Mount Everest-sized boulders triggering mass annihilation, no one is safe from their wrath. And some of these intruders are not extraterrestrial. They're actually man-made cosmic junk. Take cover as we investigate meteorites and space debris, the deadly stuff that falls from space. (11:39 p.m.) October 6th, 2008. The Catalina Sky Observatory in Arizona notices something it hadn't seen before. An asteroid the size of an SUV is screaming down towards Earth at over 27,000 miles per hour. An alarm sounds throughout the international scientific community. Is this asteroid on a collision course with Earth?
This object was special because it was probably going to impact the Earth. And over the course of the next 21 hours, 500 observations were made of the object to try to exactly calculate its orbit.
At NASA's Jet Propulsion Laboratory, Steve Chesley gets the urgent wake-up call. Everyone wants to know when and where this rock will touch ground.
They sent me the data. I rushed into the office rather excitedly and spent the next couple of hours trying to get my arms around the problem and running the numbers. And I reached the conclusion it was a 100% chance of impact.
Chesley calculates the collision will occur in less than 13 hours, approximately 5:45 a.m. Eastern African Time. Its target, the Nubian Desert in northern Sudan.
We had really expected or anticipated the discovery of an asteroid that was going to hit the Earth before impact. With time to react and time to predict the location of the impact, it was very extraordinary. Never seen it before.
It was countdown to impact.
Steve Chesley.
With no time to stop this runaway space rock, emails went out to alert those on the ground and in the air. 5:45 a.m. The moment has arrived. A commercial pilot is flying over Sudan. He witnesses a fireball smack right into the Earth's atmosphere with the energy of about 1,000 tons of TNT.
As it entered the atmosphere, it started to burn and brighten. At some point, the stresses on the body became so fantastic from the atmospheric pressure that it just exploded. That explosion would have sounded like a sonic boom.
On the ground, 23 miles below, Sudanese people returning from morning prayers hear the frightening sonic roar. Witnesses see a brilliant fireball, followed by mysterious flashes of light streak across the sky. Scientists had hoped the asteroid wasn't heavy enough to completely penetrate through the Earth's atmosphere and wreak havoc on the ground. Satellites track the fiery explosion, but there is little indication that any fragments survive.
So there is a possibility that people could be frightened by such an event, but the risk of injury is really very low from something so small.
And Steve was correct. There were no reports of injuries or damage due to falling debris in the remote region. Planet Earth was spared from a potential disaster, partly because the region was so remote and the impactor was small. But the story doesn't end here. December 2008. Astronomer Peter Yeniskis organizes a search and recovery team from the University of Khartoum in Sudan. he's determined to find the unlikely. Meteorites, the surviving fragments of the asteroid named 2008 TC3.
We had a busload with students who were all eager to go and search. We drove 29 kilometers into the desert to go to the area close to the explosion to look for the smaller pieces that might have survived.
The meteorite hunter's only guide is a map of the Nubian desert with the projected approach path of the asteroid.
They basically used my trajectory and the ground track that I had laid out on the desert floor as a guide for their search.
Lined up everybody about 20, 30 yards apart, and then started walking down the desert in line, searching for things that were black.
But spotting small charcoal-like stones on the rocky desert surface is akin to finding a needle in a haystack. As the sun begins to set on the first day, the team is about to walk away empty-handed when a student suddenly comes forward with a suspicious rock.
A student called Mohammed Alamin had this little rock in his hand that was clearly a meteorite. It had a beautiful black fusion crust around it, and it was undoubtedly a meteorite. And then everybody started being excited and shouting and singing and waving their hands.
280 meteorite samples were eventually recovered, equaling 11 pounds, which for planetary scientists was like hitting pay dirt.
This was one of the meteorites that was recovered. Not much bigger than this. We think that a lot of these meteorites, when they came out of the explosion, were tumbling very rapidly, and that resulted in breaking of the meteorites when it was still up in the air.
2008 TC3 is the first asteroid ever observed in space, which was later found on the ground. Scientists are calling it the first asteroid sample return mission.
It's the first time that we've actually detected something in space, figured out that it was going to hit the Earth, figured out where it was going to hit the Earth, and we actually saw it hit the Earth. We've even recovered pieces of it. That's remarkable.
This whole experience was really fantastic for us. This was an excellent test for what we're really preparing for, which is the possibility of having to deal with a larger impactor sometime in the future.
Planet Earth may not be so lucky the next time. Scientists now suspect 2008 TC3 came from a piece of a much larger rock from the asteroid belt, a region between Jupiter and Mars where asteroids and comets take up residence. In this crowded galactic neighborhood, these fossil relics from the formation of the solar system occasionally collide with each other and explode into smaller pieces. It's these fragments that can migrate towards Earth.
A bullet can provide a pretty good stand-in for one asteroid striking another in terms of its impact speed. Asteroids in the main asteroid belt will run into each other at speeds of over 11,000 miles per hour. Now, a bullet traveling out of a rifle can be a good analogy for that because they will leave a rifle barrel at speeds, maybe a fifth that. So it doesn't just fragment, it literally blows itself to pieces. Okay, we'll head downrange and actually set up our little artificial asteroids at a safe enough distance to shoot. Since real asteroids are hard to come by, we're going to use a couple of stand-ins today.
These bullet impacts are comparable to the collisions in the asteroid belt.
Let's see what our results are here. This is actually rather typical of the results of an asteroid impact, where you tend to have a few large pieces of debris, several medium-sized pieces, but nature is very good at making lots and lots of little debris. These little kilometer-sized fragments are what we actually see today as the near-Earth asteroids, these fragments which have worked their way in from the main asteroid belt, approaching the inner solar system, passing near our planet, sometimes impacting our planet.
These near-Earth objects, or NEOs, have transformed our near-space environment into a danger zone.
The speeds with which objects are running around in the inner solar system is it's much akin to actually a bunch of cars driving crazily down a highway. The vehicles themselves are traveling at high speeds. When they cross lanes without looking and perhaps running into each other, they are hitting at equally high speeds. And that's kind of like objects moving on their own independent orbits around the sun.
Every few hundred years, Earth gets hit with rocks the size of a football field that can destroy entire cities. But every 500,000 years, we get struck with boulders the size of mountains that could ignite global disasters. The Earth's atmosphere, a layer of gases surrounding our planet, incinerates most material. But occasionally, larger, heavier objects slip through.
As soon as they enter the Earth's atmosphere, they get slowed down, decelerated by the atmosphere, and they lose pretty much all of the velocity with which they entered. And during that time is when you see the fireball event. But once they lose that velocity that they came in with, they essentially just fall pretty much at terminal velocity onto the Earth's surface.
When asteroids hit the Earth's atmosphere, they become meteors, bright fireballs in the sky. If they make it to the ground, they're called meteorites. Over the past century alone, meteorites have struck homes, vehicles, and even people. In 1954, an 8-pound meteorite crashed through the roof of a home in Sylacauga, Alabama, and hit a woman in the hip, leaving her with nasty bruises. In October 1992, amateur videos caught a fireball flashing across the skies above several Atlantic states. The 27-pound meteorite eventually crushed the back end of a car in Peekskill, New York. In November 2008, a police dash camera recorded a bright meteorite explosion in the skies over Alberta, Canada. These caught-on-video impacts prove that things really do fall from the sky. What's even more startling is the physical evidence of much bigger impacts, ones that have caused global catastrophes in the past and may ignite a cosmic Armageddon in the future. Earth was not always an ideal address for human beings. During its infancy, 3.8 billion years ago, the third rock from the sun was a cosmic war zone. During this brief period, called the Late Heavy Bombardment, billions of leftover debris from the formation of the solar system pummeled our planet at rates up to 20,000 times higher than today.
What happened is that Jupiter and Saturn, the two giant planets in our solar system, went into what's called a gravitational resonance with one another. So Jupiter made 2 complete orbits around the sun for every single orbit made by Saturn. And when that happened, it rearranged the entire solar system. It reshuffled Uranus, Neptune, Jupiter, and Saturn, and moved the giant planets farther out. When that happened, that just sent a volley of comets and asteroids rocketing into the inner solar system.
At the same time, these rocky bodies helped to mold our baby planet to the shape it is today. Here are the battle scars. Only 170 impact craters are still visible on Earth. Weather, water, and plate tectonics have erased most traces of ancient cosmic violence. But proof of Earth's tumultuous past lies on the Moon, which was formed at the same time, but lacks plate tectonics and other erosion processes that tend to erase the evidence.
The Earth itself has been bombarded every bit as much as our nearby moon. If you look up at the moon in the sky and you see its cratered surface, you have to imagine our own Earth cratered and battered to at least that degree, and in fact, because we're a bigger target in space, even more.
By counting craters on the moon, scientists can learn about the number of impacts on the nearby Earth, past and present.
Scientists can learn about the sizes and compositions of asteroids that impact the Earth by studying the characteristics of the craters that they create. So we're going to try and demonstrate that today by tossing some weights into the sand on the beach here, and we're going to see if we can come up with a relationship between the size of the weight and the size of the crater that it creates. Based on my measurements, I calculate that this beach was impacted by 3 rocks 10 inches in diameter, 5 rocks that were 6 inches in diameter, and 11 2-inch diameter rocks. This technique of measuring the size and frequency of craters on this beach is very similar to the technique that scientists use to understand the frequency of impacts throughout Earth's history.
Today, the best preserved impact craters exist in dry desert regions around the world. Meteor Crater, located near Winslow, Arizona, is one of the lasting reminders of the destruction caused by objects from space. And scientists are just cracking the surface of understanding the repercussions of these ferocious events.
Okay, lights.
Okay, do we want to back one off to 250,000?
Planetary geologist Pete Schultz formulated a new experiment to simulate what impact craters look like under the surface.
1.1 feet.
At the Vertical Gun Range at NASA's Ames Research Center, Schultz is using a massive 30 caliber light gas gun that shoots projectiles at various targets inside a vacuum chamber.
Today, we're going to try to look inside a crater as it forms. And to do this, we're going to use a clear block. It's transparent, so we actually get to watch the crater as it grows, but from the inside rather than from the outside. This little bead is simulating an asteroid that's going to slam into the surface of the Earth. So let's get inside. We're in the impact chamber. This is where everything happens. The little projectile bead is going to be coming in at around 4 miles per second. We're going to hammer this transparent block. We're going to be looking at everything that happens below the ground when an asteroid hits the surface of the Earth.
Outside the chamber, high-speed cameras will document the deep impact from various angles.
Are the Shimatsus all up down there?
In the control room, Schultz watches the monitor with nervous anticipation.
High voltage?
The vertical gun launches the glass bead projectile into the acrylic block.
Sweet. Wow, okay. That is just frickin' gorgeous.
The experiment was a smashing success.
Kapow! So here we actually have the impact, but now we see this vapor plume. This is really hot gas. It's about a temperature close to the surface of the sun. And then as it moves away, it cools, and now we begin to form the crater with the ejecta coming out. And we're watching the crater actually begin to form on the inside. That is awesome. Okay, I want to see what we did. Oh man, did we bust this up. Now we can look to see how these cracks develop through time. So if this were a big impact, these cracks would grow where the entire crater could then collapse inward and fail.
Impact experiments at the Vertical Gun Range shed light on the large-scale destruction caused by asteroids that have fallen from space.
When we see an impact, it's not just the cracks and cracking. You will also see the vapor plume expanding. That affects life. That affects survival. If this impact occurred on Earth and was large in scale, it would simply fry the atmosphere. It would send debris out, and as it hits the Earth, again, it would cause more devastation.
Scientists have discovered that impacts from space have affected the evolution of life on Earth.
We know that, in fact, the flux of meteorites hitting the Earth was much higher in the past than it is today. And in fact, there have been known instances, for example, the large impact event 65 million years ago at the Cretaceous-Tertiary boundary.
$65 million years ago, an asteroid the size of Mount Everest struck the Yucatan Peninsula in Mexico with the energy of a 100 million megaton bomb. It created a 100-mile wide crater underwater that was finally discovered in the 1980s. Scientists have determined that the asteroid impact ignited atmospheric events that may have led to the mass extinction of 75% of all prehistoric species, including the dinosaurs.
There were a lot of potential effects that could have led to the extinctions. Heating of the atmosphere, for instance, by the ejecta, perhaps leading to wildfires. The poisoning of the atmosphere from the gases produced from the vaporized asteroid. It was every ecological disaster you could think of all happening at the same time.
But was this the last time an asteroid triggered a mass extinction? A controversial new theory suggests a space rock was responsible for the disappearance of the Ice Age megamammals of North America. Scientists are dying to know what happened 13,000 years ago. The Ice Age was slowly ending. The North American continent was inhabited with big beasts like the woolly mammoth, mastodon, giant ground sloth, and the short-faced bear. But something caused 35 major groupings of species to vanish from the fossil record. Many think the ancient Clovis people, a hunter and gatherer society, killed off the mega mammals. But startling new evidence suggests that an object from space may have led to the demise of the giant creatures.
13,000 years ago, the climate changed suddenly, rapidly, and dramatically. It looks like there was some type of extraterrestrial event, whether it was a large meteorite, an asteroid, or a comet exploding in the atmosphere. And all of a sudden, the planet was thrown back into a little ice age.
North America experienced a brief return to Ice Age conditions. So could there be a connection between this cold snap and the disappearance of the mega mammals? Archaeologist Ken Tankersley claims to have dug up evidence of a possible cosmic impact in Sheridan Cave, located in Cary, Ohio.
Now, let's see what you found so far.
It's one of only 12 known sites that have been precisely dated to the time of the late Pleistocene extinction, which was the end of the last ice age. In this deep cavern, Tankersley and his team have discovered the burned remains of more than 60 species of plants and animals from that time period, including hunting weapons of the Clovis culture.
I don't believe it. This is a Clovis bone point. It's manufactured from a megamammal rib, probably a large animal such as the American mastodon. What's fascinating about this specimen is the person who manufactured this likely witnessed the event 13,000 years ago.
Tankersley says that most of the bones he's uncovered underwent intense burning that couldn't have been caused by a mere forest fire. He says it had to have been from a colossal explosion, the kind generated by an Earth impact. And the archaeologist says he's found the smoking gun.
Oh, look what we have here.
It's hidden in a dark geological layer of dirt called the Black Mat, which dates back to 12,900 years ago. This layer has been uncovered in more than 50 locations in North America.
Note this black area. Let's see if I can trowel through here and bring out some of the more dark areas. Oh, nice. We're literally at this spot looking at the contact of the end of the last ice age. And this oxidized layer above it, this is where the mega mammals go extinct.
Within this sediment layer, some scientists claim to have found key pieces of evidence that point to a cosmic impact. Carbon spherules created by intense fires. Shocked diamonds formed through extreme temperatures and pressures. Lonsdale-ites, rare hexagonal-shaped diamonds that are only found in meteorites. And micrometeorites, minuscule pieces of iron and nickel that come from outer space.
If we take a magnet and run it across this oxidized layer, my guess is we'll probably pick up micrometeorites. You can see how the sediment's adhering. And just as the magnet picks up iron from this layer, so does the magnet adhere to this meteorite. And this suggests, because we have a high concentration of micrometeorites in this layer and a complete absence above or below, and it's at the event of 13,000 years ago, something dramatic occurred here.
We know that all over North America there is a thin layer of dust and particles just before that black mat formed. That indicates that something happened right before the event, that is the climatic change. What is it? We still don't know exactly. All we know that something happened.
To date, no impact crater has been found. But a space rock doesn't have to reach the ground to generate mass devastation. In 1908, a rocky body slammed into the atmosphere 6 miles above Siberia's Tunguska wilderness. It released energy yielding about 5 megatons of TNT.
You can imagine what it feels like to do a belly flop off of a high diving board and you smack into the water. A small, weak, rocky asteroid will kind of undergo a similar sort of feeling as it very quickly is decelerated and braked in the dense lower atmosphere.
Immediately after the Tunguska airburst impact, an intense shock wave and hot air blast traveled to the ground and spread outward. It engulfed almost 1,000 square miles of forest. Some scientists propose that a similar scenario may have contributed to the extinction of the North American megamammals. And a comet, not an asteroid, may have been the culprit. Unlike asteroids, these dirty snowballs contain more ices and gases that tend to break up before reaching the surface.
When the theorized comet came down into the Earth and would have exploded in the atmosphere, it would have distributed amongst the ejecta that was created beneath it. It would also have seen a great variation in the deposits left behind. There would have been intense burning over a large area. Anything within the impact zone, of course, would have been devastating. At the same time, however, it would not have had immediate impact for the rest of the planet, just within the impact area itself.
This so-called Clovis comet theory suggests that profound climate changes led to the eventual extinction of the mammoths from North America. However, contrary to popular belief, a small number actually survived in various regions of the world up until around 2000 BC. And archaeological evidence indicates that the Clovis culture didn't go extinct from this alleged impact. Rather, they adapted to their changing environment.
When the large game animals that Clovis people were hunting disappeared from the landscape, people had to change the way in which they were hunting and gathering.
We may never know with certainty whether a near-Earth comet caused the Clovis event. But would modern man learn to survive after an Earth impact? We may eventually be put to the test. At this very moment, meteorite scientists scour the landscape in search of these messengers from the sky. These space rocks hold clues to impacts of the past, and as scientists are now discovering, clues to what is coming in the future. Mass extinctions, mile-wide craters, scorched landscapes, all created by objects from space. Meteorites have been intruding on our planet since the formation of the solar system. So where do we typically find these rocks?
Most meteorites, they're more easily found in dry desert regions of the Earth. For example, in the Saharan desert or even the cold deserts like Antarctica, where there's not a whole lot of vegetation or there's not a whole lot of other rocks to confuse you. However, meteorites fall everywhere on Earth with equal probability.
Cosmochemist Meenakshi Wadhwa has traveled the world in search of meteorites and now oversees the largest university-based meteorite collection in the world.
We're here looking at the collection of meteorites in the Center for Meteorite Studies at Arizona State University. There's basically 3 different kinds of meteorites. You can have stony meteorites, stony iron, or iron-rich meteorites, but all 3 kinds have at least some amount of metal. And so you can distinguish terrestrial rocks from meteorites by the content of metal in meteorites. The other way to actually distinguish a meteorite from a terrestrial rock is that you'll actually see a fusion crust on meteorites that forms on these objects when they're falling through the Earth's atmosphere.
Most of the meteorites recovered originated in the asteroid belt between Jupiter and Mars. But nearly 4 dozen actually came from our moon and the planet Mars.
The idea there is that you probably had a large asteroidal body that impacted the moon or Mars and ejected pieces of the crust of the moon or Mars. And these ejected pieces probably fell into these unstable Earth-crossing orbits, and eventually pieces made their way to the Earth that way. This is a piece of a lunar meteorite, and we believe it came from the Highlands portion of the moon. And we know that this is actually a lunar meteorite because we can compare this with actual samples that were brought back by the Apollo missions in the late 60s and early 70s.
Meteorites are precious research subjects. Although they've destroyed life time and time again, they may also have provided the chemicals needed for life on Earth.
This is possibly one of the most well-studied meteorites in the world. It fell in 1969 in Mexico. And an interesting thing to note about this rock is that these white grains are possibly some of the oldest solids that formed in our solar system as our solar system was forming 4.5 billion years ago.
These white grains, combined with the atmospheric chemicals and organic compounds on Earth, may have formed a mixture of amino acids, the essential elements of life.
So meteorites have played a very important role in possibly the formation of life on our planet and certainly the evolution of life on our planet.
Meteorites may have once provided the necessary components for living things. but they can be a source of grave concern when they hurtle down from space without prior warning. September 19th, 2007. A fiery meteorite streaked down from the sky and impacted the soft soil near the Peruvian town of Caracas, which borders Bolivia. Debris flew over 600 feet as the meteorite left a crater over 15 yards wide and 15 feet deep.
There was a gentleman riding a bicycle and he was knocked over. Another person looking the other direction quickly turned around and saw this thing hit with a large plume rising above. In talking with the locals, the villagers, they had no idea except they thought maybe this was some form of military action. You know, they're very close to the border of Bolivia.
Scientists reassured the locals that a meteorite, and not a missile, caused the impact crater. But immediately after the event, many villagers complained about headaches and vomiting.
They literally became ill, most likely because of sulfur or because of the fine dust that was inhaled. The vapor probably came from the material that was following the meteorite as it was coming through. It was melting, it was vaporizing as it passed through the atmosphere, and it probably, when it hit, caused some additional release of gas.
But could a space rock actually deliver harmful elements to Earth? Sci-fi movies and conspiracy theorists have proposed that meteorites could seed our planet with lethal bacteria or viruses. But what's fact and what's fiction?
The probability of this happening is very, very, very small. If that rock made it to Earth and somehow that microbial life form survived, it would find our atmosphere very toxic. Any microbe that evolved in an anaerobic and a non-oxygen environment is not going to survive long in oxygen.
The possibility that the Peruvian meteorite committed cosmic biological warfare is remote. But had this small stony meteorite impacted a nearby village, the aftermath would have been much different.
This would look like somebody had planted a roadside bomb. It would have had that effect. It opened up a hole so large that it would have swallowed several cars.
The Peruvian meteorite impact once again illustrates the unpredictability of things that fall from the heavens. And space rocks aren't the only objects that can cause bodily harm. Up to 200 heavy objects hit our planet each year. And they're not extraterrestrial, they're man-made.
By GNC.
2 minutes to place.
February 1st, 2003. The space shuttle Columbia was about to conclude its mission in space when disaster struck. The vehicle disintegrated during re-entry into Earth's atmosphere. Debris fell over Texas, Louisiana, and Arkansas. All 7 crew members perished.
Because of re-entry heating, it got hotter as it came into the atmosphere. Some critical components failed. That caused an overall failure of the entire spacecraft, which spread debris over a large footprint.
Spacecraft re-entry disasters are rare, but space debris is not. Since the beginning of the space age, rockets have carried thousands of satellites into orbits around our planet. As a result, we've littered space with spent rocket stages, defunct satellites, fuel tanks, as well as nuts, bolts, and fragments from collisions and explosions with other debris. This abandoned space debris hovers over our planet like a cosmic garbage dump, and some will eventually fall back to the Earth. The question is when and where.
Things that re-enter the atmosphere, they do have a risk. The real risk is that something falling through the atmosphere will hit a person on the ground. 5,400
tons of space junk has already crash-landed on Earth. In 1979, Skylab, the first space station, scattered debris across the Indian Ocean and parts of Australia. In 1997, a DVD-sized piece of smoldering metal fell from the clouds and brushed the shoulder of a woman near Tulsa, Oklahoma. She wasn't injured, but hundreds of miles away, this 570-pound stainless steel tank landed next to a farmer's house in Texas. Both were pieces of debris from the same stage of a Delta II rocket.
It's a piece of debris from a launch stage that was in orbit for about 9 months and re-entered over the northern part of the United States and Canada. Came down and left several fragments of debris around. This was the largest piece.
At the Aerospace Corporation in El Segundo, California, scientists study space debris to find out what materials survive re-entry and why, and how to minimize future hazards.
This is remnants of a stage that put a GPS satellite into orbit. This was found in Saudi Arabia. This one is made out of titanium, which is a very high melting point material, and that's one reason why this one survived so nicely. And this was traveling again on the order of probably 150 miles an hour when it hit the ground.
Why do objects fall back to Earth? Most space debris resides in low Earth orbit, approximately 600 miles above our planet's surface. In space, objects can stay for tens to hundreds of years because there's no air resistance. But they will eventually undergo orbital decay. They will lose energy because there's very little atmospheric drag, and the Earth's gravity will tug them back down into its atmosphere.
Satellites fall back sometimes quickly and sometimes over a long period simply because they begin to touch a little bit of the atmosphere, enough of the atmosphere that there's an increasing force over a long period of time, and that small force acting over a long time will basically drag them out of orbit, and they will eventually re-enter.
Most debris burns up during atmospheric re-entry and vaporizes. However, some pieces are made of stronger components such as stainless steel and titanium, which can survive tremendous heat. Once below the dense regions of the atmosphere, they literally free fall to the ground.
It'll hit at a very low velocity, say 150 feet per second or 150 miles an hour, something like that. And so that's the problem. So you're basically slowing something from an orbital speed down to essentially nothing in a relatively short time.
Main engine start.
The international space community now imposes new design requirements for most objects, including a propellant system to ensure controlled re-entries over water.
Basically, the international community has agreed that an acceptable level of risk for a re-entry is around 1 in 10,000. That means that if you did a particular re-entry 10,000 times, the likelihood is that you'll hit one person on the planet. And so if you exceed that threshold, the objective is that you should re-enter that piece of hardware into a safe area like the ocean.
But new guidelines won't have any effect on the thousands of pieces of old debris already in space.
Unfortunately, we have a number of objects in space still which were not designed when that requirement was around, and they still are slowly coming down. So it'll be a while before some of these things take effect.
It's no longer a sci-fi fantasy. Extraterrestrial and man-made things continue to fall to Earth. We constantly need to search the skies for objects that could decimate a neighborhood, or even worse, end human civilization.